Hi everybody, in this lesson we're going to talk about how to use the sum and difference identities for cosine, and I'm actually going to show you how these identities came about, and I'm also going to show you how to use them to simplify expressions and how to verify identities. And we'll also take a look at where the cofunction identities came from. So let's get started. We'll take a look at an angle on a unit circle. So our radius is 1 because this is a unit circle, and we'll call this angle A. And I'll say that angle A goes through the unit circle at a point that we'll call S, and the coordinates for this point S would be cosine A comma sine A, because remember, on the unit circle, every point on the unit circle has a x coordinate equal to the cosine of the angle and a y coordinate equal to the sine of the angle. So, we only used this for quadrant angles, but it's actually true all the way around the circle. And so these are the coordinates of point S. And then I could draw a second angle B, and we'll call the point where it meets the unit circle here, we'll call that Q. And so these xy coordinates would be cosine B comma sine B. Now this angle in between them is angle A minus angle B. You can see, if we take A and subtract B from it, what's left here in purple is angle A minus angle B. Okay, now let's look at the other coordinate system. It also is a unit circle, and I've drawn here the angle A minus B, so it's the same size as this angle here, but it has its initial side on the positive x-axis. So the xy coordinates of this point that we'll call R would be cosine of A minus B, comma, sine of A minus B. And then out here on the positive x-axis, the initial side would have a coordinate of 1 comma 0, and we know that's 1 comma 0 because remember, this is a unit circle, so the radius of this circle is 1. Now if we draw a line from point S to point Q, like this green one, and we draw a line from point R to point P, like this green one, these two lines should be the same length, because the circles are the same size and the angles are the same size. Therefore, the distance from S to Q is equal to the distance from R to P. And since we're talking about distance, let's take a look at the old distance formula that you may remember from algebra. And it's really just a fancied up Pythagorean theorem. The distance between 2 points is the difference between the x's squared plus the difference between the y's squared, square root. So you can see, I'm sure, the similarity to the Pythagorean theorem here. It's the sum of two squares, square root. So let's copy that on a new slide so we'll have a little more room to work. Alright, so we figured out that the distance from S to Q should be the same as the distance from R to P. So let's use the distance formula to figure out the distance from S to Q. So the distance from S to Q should be the difference between the x's, so cosine A minus cosine B squared, plus the distance between the y's, so sine A minus sine B squared, all square root. And the other side would be the distance between the x's, so cosine of A minus B minus 1 squared, plus the difference between the y's, so sine of A minus B minus 0 squared. Right now we have to go back and work out each of these squared binomials. So we know that this one is going to be cosine squared A minus 2 cosine A cosine B plus cosine squared B. That's just what you get when you use the FOIL method on cosine A minus cosine B times itself. And now we'll square sine A minus sine B. So sine squared A minus 2 sine A sine B plus sine squared B, and that equals cosine squared A minus B minus 2 cosine A minus B plus 1. And again, that's just using the FOIL method to square this binomial. And then this one is not really a binomial because it's minus 0, so we'll just get sine squared of A minus B. Now, since the left side and the right side are both under the radical, we can actually just lose the radicals. And let's see what's left here. We'll go to a new page and copy this equation over so we can see how it simplifies. Okay, the cosine squared A plus sine squared A together makes 1. Cosine squared B plus sine squared B together makes 1. Those are Pythagorean identities. And then we have minus 2 cosine A cosine B minus 2 sine A sine B equals, on the right side we have cosine squared of A minus B plus sine squared of A minus B. We know that cosine squared plus sine squared is always equal to 1. And then we have another 1. And then we have minus 2 cosine of A minus B. Now, of course, here 1 plus 1 is 2, and over here 1 plus 1 is 2. Alright, now, since every term is a multiple of 2, we can just divide both sides by 2 and cancel each of those 2's right out. Okay, so I've divided everything by 2. 2 divided by 2 is 1. This term divided by 2 gives us cosine A cosine B. This term divided by 2 gives us sine A sine B. And this term divided by 2 gives us 1. This term divided by 2 gives us cosine of A minus B. Alright, now you can see we're going to subtract the 1's from both sides, and we'll be left with negative cosine A cosine B minus sine A sine B equals negative cosine of A minus B. They're all negative, so let's multiply both sides by negative 1 to make all the terms positive, and we have our identity for cosine of A minus B. Notice that the cosine of A minus B formula contains a plus sign in between the two terms. Alright, now let's take a look at the sum identity for cosine. So we'll just start with the difference identity that we already figured out. And what if instead of B we had negative B? So everywhere that I used to have B, I've replaced it with negative B. And now we can say that minus negative makes positive. Okay, here, if you remember your negative angle identities, the cosine of negative B is the same as the cosine of positive B. So that does not change. On this term, where we have sine of negative B, the sine of negative B is equal to negative sine of positive B. So if we just pull that negative right out of there, we get sine of A times negative sine of B. Well, we know that positive times negative gives you a negative, so that's going to make this become a minus sign. And there's our identity for cosine of A plus B. Here are the two identities just side by side so you can see them. You need to copy them in your notes. You do not have to memorize these. You just need to be able to use them in a problem. So here's our first example. We want to use a sum or difference identity to find the exact value of cosine of 15 degrees. So the trick is to think of 15 degrees as either a sum of two angles or a difference of two angles, and it needs to be two angles whose exact function values you are familiar with. Well, that kind of limits us to 30, 45, and 60. So if you subtract 60 degrees minus 45 degrees, or if you use 45 degrees minus 30 degrees, either one of those will give you 15 degrees. So I'm just going to go with 60 degrees minus 45 degrees here. And this is the identity we're thinking of, because 60 minus 45 is 15, then I can let 60 degrees be A and 45 degrees be B. So I've copied everywhere I had an A, I've copied in 60 degrees, and everywhere I had a B, I've copied in 45 degrees. And now these are all values that we should know by heart. So you remember that the cosine of 60 degrees is 1/2. The cosine of 45 degrees is square root of 2 over 2. The sine of 60 degrees is square root of 3 over 2. And the sine of 45 degrees is square root of 2 over 2. Now it's all downhill from here. The trigonometry is finished. All we have to do is the arithmetic. So we'll multiply these two fractions together, multiply these two fractions together, and then we'll see where we are. 1 times square root of 2 is square root of 2, and in the bottom 2 times 2 is 4. For the other term, square root of 3 times square root of 2 is square root of 6, and in the bottom 2 times 2 is 4. So when you multiply radicals together, you just multiply what's under the radicals and leave the answer under a radical. Now when you add radicals, it's totally different. When you add radicals, it has to be similar to like terms. These are not like terms. They're not like radicals, so we cannot add these together. Square root of 2 plus square root of 6 is not square root of 8. You just have to leave it as two separate terms. But I did combine them into one fraction. Now let's go ahead and find the exact value of cosine of 5 pi over 12. Okay, it might be helpful to you to change 5 pi over 12 into degree form. So if you remember, we can change from radians into degrees by multiplying by the conversion factor 180 over pi, and that gives us 75 degrees. So if I'm trying to think of 75 degrees as a sum or difference of two of my known angles, 30, 45, and 60, then it's easy to come up with 75 equals 30 plus 45. So the cosine of 5 pi over 12 equals the cosine of 75 degrees, which is the cosine of 30 degrees plus 45 degrees. Now we can use our cosine of A plus B formula, or identity. Here it is. Okay, so this is the identity, and then if I let the two angles be 35 degrees plus 45 degrees, everywhere I had 30 degrees I can substitute for A, or everywhere I had A I can substitute 30 degrees in, and everywhere I had B I can substitute 45 degrees in. And now it's just a matter of filling in these values. The cosine of 30 is square root of 3 over 2. The cosine of 45 is square root of 2 over 2, minus sine of 30 is 1/2, and sine of 45 is square root of 2 over 2. Now again, radical multiplication means we multiply what's under the radicals. So top times top, bottom times bottom. And for the other two fractions, 1 times square root of 2, and in the bottom 2 times 2 is 4. And so now we can just subtract these, but we cannot subtract the radicals, or we can't combine the radicals. We can put them together in one fraction. So there's that one. Now I think you should be aware that if you take your calculator and punch in cosine of 75 degrees, you're going to get a decimal value. We can't use that as the answer to this question because they asked for the exact value, but we can at least make sure that the decimal value given by the calculator is the same as the decimal value of this expression. So if you punch into your calculator square root of 6 minus square root of 2, press equal, and then divide that answer by 4, it should give you the same decimal value as cosine of 75. Now here is an example that looks a little different. They've asked for the exact value of cosine 87 times cosine 93 minus sine of 87 sine of 93. And if you'll look at your identity sheet, you'll recognize this looks almost exactly like one of our identities. In fact, it looks like the cosine of A plus B. See how it fits exactly, even down to the sign, and it does have to fit exactly. If this identity fits our expression exactly, that means that 87 can be A and 93 can be B. So what we really have here is the cosine of 87 plus 93. Now 87 plus 93 is 180. So this expression here is equivalent to the cosine of 180, and we know from the unit circle that the cosine of 180 is -1. And if you don't remember that, I'll just kind of remind you here. On the coordinate system, if you had a unit circle, 180 degrees would be right here on the left side, where the coordinates of that point are -1, 0. And remember, cosine is the horizontal coordinate, so that would be the -1. Now we're going to talk for a few minutes about the cofunction identities. So I have here cosine of 90 degrees minus x, because you know that 90 minus x would be the way to find the complement of x. So you can think of 90 minus x as complement of x. And because this is in a form of a minus b, let's use our cosine of a minus b identity. So it's going to be cosine of 90 times cosine of x plus sine of 90 sine of x. Now the cosine of 90 we know. Cosine of 90 is 0. And cosine of x, of course, is unknown. Sine of 90 is 1 times sine of x. 0 times anything is 0. And 1 times sine of x is sine of x. So it looks like the cosine of 90 degrees minus x is equal to sine of x. In fact, that is one of our cofunction identities. Here it is. The cosine of 90 degrees minus x is equal to the sine of x, or in this case, theta. We have seen these cofunction identities before in a previous chapter, so we won't derive them all, but you saw how we used the cosine of a minus b to come up with this relationship. Then the sine of a complement is equal to the cosine of the original angle. Tangent of a complement is equal to cotangent of an original angle. And so on, all 6 of these, you know. And if you are trying to work in radians, you can just replace the 90 degrees with pi over 2 and just keep going. Okay, for our next example, we will find one value of theta or x that satisfies each of the following. So the first one says cotangent of theta equals tangent of 25. So our identity says cotangent of theta equals tangent of 90 minus theta. That means that 25 must be equal to 90 minus theta. If you solve this by adding theta to both sides and subtracting 25 from both sides, you'll see that theta equals 65 degrees. So, of course, we already knew that from a previous chapter. We knew that the cotangent of 65 would have to be equal to the tangent of the complement angle, which would be 25. Let's do it again for part B here. We have sine of theta equals cosine of -30. So using our identity, the sine of theta is equal to the cosine of 90 minus theta. That means that -30 must be equal to 90 minus theta. Add theta to both sides. Add 30 to both sides, and we get theta must equal 120. Now, if you think about it, 25 degrees and 65 degrees add up to 90. -30 and positive 120 add up to 90. And I bet you on this next one, these two angles add up to 90 degrees. You know, if you're thinking in degrees. So let's first, this is in radians, so instead of 90 degrees minus x, we'll use pi over 2 minus x. So the cosecant of pi over 2 minus x is equal to the secant of x. So these two sides are the same. That means 3 pi over 4 must be equal to pi over 2 minus x. We'll add x to both sides and subtract 3 pi over 4 from both sides. And now it's really no trouble here. We're doing 1/2 minus 3/4. So we do a little common denominator thing, multiply this by 2 over 2. 2/4 minus 3/4 gives us negative 1/4. So 2/4 pi minus 3/4 pi gives us negative 1/4 pi. And I've picked out just a couple more from the homework to go through with you. This one says, write each function value in terms of a cofunction of a complementary angle. So the instructions are telling you exactly what to do. The cosecant of 14 degrees and 24 minutes is equal to the complementary function, or the cofunction, of the complementary angle. So the cofunction of cosecant is secant, and then the complement of 14 degrees and 24 minutes is going to be 90 minus 14 degrees and 24 minutes. So you can do this on your calculator. Remember, we had that degree, minutes, seconds button. 90 degrees minus 14 degrees and 24 minutes is 75 degrees and 36 minutes. And of course, we went from cosecant to secant, from angle to complement. Okay, this one's similar. The sine of this angle has to be equal to the cofunction of the complement angle. So the sine of 142 degrees and 14 minutes is equal to the cofunction, the cosine, of 90 minus 142 degrees and 14 minutes. And if you punch that out on your calculator, you'll get the angle that you're looking for has to be negative 52 degrees and 14 minutes. So the sine of 142 degrees and 14 minutes is equal to the cosine of negative 52 degrees and 14 minutes. In example 3, it says write the cosine of 180 degrees minus theta as a trig function of theta alone. So we can't have 180 minus theta in the parentheses in our answer. We have to have just theta in the parentheses. So this looks like A minus B. Let's plug it into our identity. And everywhere we have everywhere we have A, we'll plug in 180 degrees. Everywhere we have B, we'll plug in theta. So it's going to say cosine of 180 degrees times cosine of theta plus sine of 180 degrees times sine of theta. Now the cosine of 180 is the x-coordinate for the left side of the unit circle, so it's negative 1. And the cosine of theta there is unknown. Sine of 180 is 0. And so, of course, this term becomes 0 because 0 times anything is going to stay 0. And we end up with negative cosine of theta. So cosine of 180 degrees minus theta is equal to the negative cosine of theta. Now, example 4 says, suppose that sine of s equals 3/5 and cosine of t equals negative 12 over 13. And both s and t are in quadrant 2. Find cosine of s plus t. You do not really have to know what s plus t is to be able to find the cosine of s plus t. All you need is our identity. And let's go ahead and plug in the parts that they've told us. They told us that sine of s was 3/5, and they told us that cosine of t was negative 12 over 13. And these two values we don't know yet, but we can find them because they told us that s was in quadrant 2 and t was in quadrant 2. So using the Pythagorean theorem, we can easily find the missing sides here and come up with the missing functions. So if you remember your good old 3, 4, 5 triangle, this missing horizontal side had to be 4. If not, you could use the Pythagorean theorem to find out. And so the cosine of s had to be negative 4 over 5, because remember in the second quadrant, cosine is negative. And then for t, we're looking for the sine of t, but we had to find this missing vertical side first. So y squared is equal to 13 squared minus 12 squared. Remember that when we're looking for a side that's not a hypotenuse, we subtract the squares. That's going to be 25. 13 squared minus 12 squared is 169 minus 144. That's 25. So that means that vertical side is 5. So the sine of t is going to be 5 over 13. Okay, so we'll just put that in right here. So we've now substituted in the two values that they didn't give us, and let's just multiply these together and see what we get. When you multiply fractions, you do top times top, so that's going to be positive 48, and bottom times bottom, that's going to be 65. Then minus 3 times 5 is 15, and 5 times 13 is 65. Now to subtract these, just subtract the tops. 48 minus 15 is 33, and the denominator is 65. Okay, here we have a verify problem. It says verify that the following equation is an identity. We know that that means we want to take one side of the inequality and use identities or substitutions or algebra on it until it looks like the other side. So the first thing I'm going to do is use a reciprocal identity to say that the secant of 3 pi over 2 minus x is equal to 1 over the cosine of 3 pi over 2 minus x. Now that I have it in cosine form, I can use my identity on it. So because this is in an a minus b form, I used the cosine of a minus b, and it says cosine A, cosine B, plus sine A, sine B. And now these 3 pi over 2, they're 270 degrees, so we know those values. The cosine of 270 is going to be 0, and the sine of 270 is going to be negative 1. If you draw it on the coordinate system and draw a dot where 270's terminal side would be, you'll see that the x-coordinate and the y-coordinate are 0 and negative 1. Alright, now 0 times cosine is going to be 0. And so we are left with simply 1 over negative sine of x. But if you notice, we've got a reciprocal here, so the reciprocal of sine of x is cosecant. So 1 over negative sine is equal to negative cosecant, which is what we wanted, so that's finished.